Welcome to Texas State University's Chemistry 2342, Organic Chemistry 2. I'm your guide, Dr. David Irvin, and I will be continuing on with Chapter 12, Part 3, Alcohols from Carbonyl Compounds. In this section, we're going to talk about creating reactions with the carbonyl where we can use organometallic reagents. So let's start talking about the organometallic reagents here. So as the name suggests, it is anything that contains a carbon-metal bond. So in general, that would look something like, we have a carbon and it can have any number of other bonds to it, but then it has a bond to a metal here. Now, in most cases, the carbon here is the more electronegative atom, and that means that it's pulling electron density away from the metal toward the carbon, giving it a partially negative charge on carbon and the partially positive charge on the metal. These are commonly denoted as an R group with whatever metal they are associated with. And the best thing about this thing is that the way they react is we react as if the carbon has a negative charge and the metal has the positive charge, which means this carbon can act as a base or as a nucleophile. The most common metals we'll talk about are lithium, magnesium, and copper, and they all have different reactivities, which is why we use different metals at different times. But those are not the only metals that these reagents are limited to. We can also use tin, silicon, thallium, aluminum, titanium, or mercury. Okay. So the three most common that we'll be using in this particular chapter are the lithium, the magnesium, and the copper species. And so in general, the general structures of that would be R lithium. And these are typically called alkyl lithiums or aryl lithiums. And they tend to be the most reactive of the set we'll be talking about right here. The next one is what we call the magnesium, organomagnesium compound, and they're also called a Grignard reagent, okay? And they typically have a structure where they also have a halogen on here. In this case, magnesium is in the +2 state, so we have the carbon acting as one of the counterbalancing anions and the halogen counting as the other counterbalancing halogen. And then the last set we have is actually a copper reagent, and the copper reagent actually bonds to two different carbon compounds here. The carbon is actually in a +1 state, giving this entire unit a -1. So we have to counterbalance that with a positive lithium here. Okay. Of this series, this is the less reactive, and therefore we actually get selectivity of this particular reagent. These are much more reactive, and they react spontaneously with a variety of different substrates. But because the copper reaction is a little less reactive, we can actually use it for different reactions where these two other reactants would react too rapidly. Okay, so moving on, let's talk about the organolithium and the organomagnesium materials and how we prepare them. They're typically prepared from their alkyl halides from their corresponding metal. So in that case, we would take one equivalent of our alkyl halide, and we would add 2 equivalents of our lithium metal. Okay, the reason we do this is that 2 electrons are transferred. 1 electron gets it to transferred to the carbon here to give us a lithium carbon bond, and then we have the lithium halide that also forms from that. So we need 2 equivalents of lithium to get this reaction to go to completion. Okay. So for example, a simple reaction on that would be to take something like methyl bromide plus 2 equivalents of lithium would yield your methyl lithium reagent and lithium bromide. Okay. These are typically done in solvents like ethers and hydrocarbons like hexanes and pentanes, but they can be done in things like diethyl ether and THF. The next reagent we want to look at is the Grignard reagent, and the Grignard reagent is one we actually can perform in our organic chemistry lab, and it's also done with an alkyl halide right here. And you only need one equivalent of the magnesium because the magnesium becomes +2. It actually does transfer 2 electrons to give us our magnesium reagent bonded to our carbon. And the magnesium is also bonded to the halogen. So there's no separate salt made like in the case of the lithium reagent. Okay. Now, once we form these, we typically form the Grignard reagents in diethyl ether. Diethyl ether helps support that complex, and it's the most common solvent used in this Grignard reagent, although THF can be used. Once we form these organometallic reagents, we have to think of that the carbon anion acts as a base. And so this base is quite a strong base, and it actually can create an acetylide ion from these reagents. In that case, what we would do is we would have just any kind of terminal alkane right here, and then by the addition of either the alkyl lithium or the Grignard reagent, we would get it to remove the proton off here and transfer it to the alkyl group to give us our acetylide ion with our metal plus whatever our alkyl group is turns into our alkane. Okay, and so for example, if we were to do this with a terminal alkyne and methyl Grignard, that would go to the acetylide ion, magnesium bromide, plus methane. So the hydrogen is transferred to the organocompound because it is such a strong base, it is removing that proton from our acetylene ion. Okay, so let's continue talking about the acid-base reaction with these organometallics. Okay. So in our generalized sense, we have our R group with something like our magnesium halide here. And of course, this is the partially negative side, and this is the partially positive side of this bond, because carbon is more electronegative than magnesium. So if we react that with something like an alcohol, where we have an acidic proton on that alcohol, the pKa of alcohols are about 15, so pKa about 15, and then when it reacts, it goes to form an alkane plus our salt of our alcohol. Okay, so if we look at the pKa of our most acidic species on the product side of the thing, we see our pKa of alkyl hydrogen is actually at 50. Okay, so that means this is the weaker acid, and this is the stronger acid. Therefore, the reaction will go in that direction to form the weaker acid. Now, when we do this same reaction with water, we'll see the same thing. If we use some alkyl lithium reagent here, plus water, water has a pKa of about 16. And when it reacts, it'll form our alkane plus our lithium hydroxide. Okay, so this being said, it's very important that you don't have any water, alcohol, or carboxylic acids, or anything with a stronger acid than the alkane being formed in these solutions, or else they will quench the reaction. Okay, so let's move on to reactions we can do with this. So one of the reactions we can do with this is it'll react with anything that has a partially positive carbon because it's acting as a nucleophile and it's acting as a base. So in the case of a cyclic ether or this epoxy here, this is the partially positive side of the bond. This is the partially negative side of the bond. So our alkyl organometallic reagent is going to attack that partially positive side to give us a ring opening reaction. Now, in the case of the carbonyl, when we look at our carbonyl, we have our partially positive side, which is the carbon, our partially negative side, which is the oxygen. And so we get attacked by that carbanion to the carbonyl carbon of this. Okay. So now What happens next depends on what kind of groups you have on your compound. So for example, if we have a carbonyl compound here, and we're going to put any R group here and then some other group here, okay? Just some random group, and we're going to react that with our alkyl lithium reagent here. And when it comes in and attacks, we can do one of two things. Well, the first thing it's going to do is form our tetrahedral intermediate, giving us our anion right here, our new sigma bond with our nucleophile, and we'll have our other group attached here. So at this point, we can do one of two things, okay? If this group here would be a poor leaving group, i.e. leave as a very strong base or a very strong anion, it will not want to leave because that's not a very good leaving group. And so what we'll do is after addition of water to the reaction, we will have an addition reaction where we've added our nucleophile to our reaction species, and it stays as our now sp3 hybridized carbon. Okay. But what if this group here makes some kind of stable leaving group, like an alkoxide or a chloride ion? If we have an alkoxide or a chloride ion here, that can actually leave and regenerate our carbonyl compound with our new substituent on there, plus our W minus. So if we have that other group there on that center carbon that can leave as a stable anion, you can have regeneration of that carbonyl by having these electrons kick in and these electrons kick out with the leaving group. Okay. So let's explore that a little bit more with the epoxies. And if you'll remember that epoxies are a nice three-membered ring. It's a very strained ring because of that three-membered, it's tetrahedral. It wants to be 109 degrees, but we've constrained it to this 60-degree angle, meaning that the entire ring strain, it wants it to spring open with the attack of any nucleophile. So if we think about the groups that are going to be also on here, they could be hydrogens, or these could be substitution groups here. And so if we react this epoxy with an organometallic reagent, such as lithium or a Grignard reagent, and then we quench that reaction with water, what's going to happen is we're going to end up ring opening that, giving us an alcohol, and our attached groups are still in the same location right here, plus our new R group is going to be added to the system. So if we attack these organometallic reagents with if we attack this epoxy with an organometallic reagent, we'll end up extending the chain by 2 and gaining an alcohol, okay? So for a specific example of that, let's go ahead and make our simplest epoxy right here. And we just have hydrogens attached to that. In our first step, we're going to attack it with a phenyl Grignard, MgBr. And then at the second step of the reaction, we're going to quench with water, and that'll generate our alcohol. And so the final product is going to be this phenyl group is going to be extended in the chain to give us this phenyl ethyl alcohol. Okay. So how does this work? Okay. So there's a two-step mechanism associated with this. The first step of the mechanism is the attack of the nucleophile on the backside of the epoxy. So let's draw a different epoxy here. We're going to do one that has different groups on it. So here we have hydrogen, and we have one that has a methyl group and a methyl group on this side here. And what we'll see is if we attack this with let's do an ethyl lithium group here, we're going to see attack by this anion, this nucleophile, and it's going to attack on the back side, which is the side opposite the oxygen, and it is going to attack on the least substituted side of the epoxy. Okay, because of sterics, it has a choice of going here or here, but the hydrogens are smaller, so the major attack route will be to the less substituted side, giving us our product after quenching with water to have a ring opened. Tertiary alcohol and our new extended chain with our alkyl lithium. Okay, so that's the ring opening of epoxies using organometallics. Let's go and look at the generalized attack onto aldehydes and ketones. In the case of aldehydes and ketones, we're going to be attacking that carbonyl carbon. So if we look at a generalized structure of an aldehyde or a ketone, we're going to have at least one R group on there. And on the other side, if it's an aldehyde, we'll have a hydrogen. If it's a ketone, we'll have another carbon here. Okay, so in the generalized reaction, we can use an organometallic reagent like a Grignard reagent here or an organolithium. The first step of this is going to be, again, attack by the nucleophile, attack by that carbon anion to yield a tetrahedral intermediate. And then when we quench with water, we're going to protonate the remaining alcohol to give us our R group. Let's signify these as our new R group plus whatever the group was already on here, whether it was an H or an R. Okay. So in this case, when we have an aldehyde or a ketone, we're using the organometallic reagent. Instead of ring open, we're actually going to do an addition across that double bond. And then the final part of the addition is adding the hydrogen from the quench water step. Okay. So let's look at this as it relates to a specific chemical. Okay. So in this case here, we're going to look at the attack of a Grignard reagent onto our substrate. And the first step of the reaction is using the nucleophile. In this case, we'll use an aldehyde. We're going to use our nucleophile, which is our anion. It's going to come in and attack the carbonyl carbon, because this is the partially positive carbon here, giving us our electrons coming up to there. So the first step gets to this tetrahedral intermediate with an anion on the oxygen, and the remaining groups stay there. The second step in that mechanism is, of course, the protonation of this carbon, of this oxygen anion, giving us our alcohol. So in the case of aldehydes and ketones, when you quench the reaction with water, you always get the generation of an alcohol. Okay. Now, we can use any nucleophile on this. We can use the Grignard reagents, the alkyl lithium reagents, or the acetylene ions to generate the same kind of addition reaction. Okay. So let's look at the ways to prepare primary, secondary, and tertiary alcohols from these substrates. Okay, I'm going to start with tertiary alcohol. And so in tertiary alcohols, you're going to have 3 different R groups attached to your alcohol. So when we start with a ketone, for example, this acetone here, and we attack it with a Grignard reagent, let's attack it with phenyl magnesium bromide, and then we quench with water, we will end up with 2 methyl groups that were already on the ketone, and the phenyl group will be attached here, yielding a tertiary alcohol. So in this case, any addition of a organometallic reagent to a ketone will generate a tertiary alcohol. Okay, so let's see how to generate a secondary alcohol. If we have most aldehydes right here, we'll have a single R group on them. I'm going to put a propyl R group here. If we attack that with something like a methyl lithium reagent, and then we quench with water, what will happen is we'll get attacked by the nucleophile onto the carbonyl carbon, and so we'll end up with something that looks like this alcohol here, where this was our nucleophile attack. This chain was already on our aldehyde, and we generate a secondary alcohol from this system. Okay, so how can we generate a primary alcohol from this? Well, to do that, we have to have already had two hydrogens on the carbonyl. And fortunately, we have our simplest aldehyde, formaldehyde, already has two hydrogens on that carbonyl carbon. If we attack that with, let's do this cyclopentyl magnesium bromide here, and then if we quench with water, again, we'll end up with a primary alcohol because we have the two hydrogens already on the carbonyl compound, and so we'll end up with our primary alcohol. So using these organometallic reagents, we can generate tertiary, secondary, or primary alcohols by looking at your starting materials, okay? So ketones will always yield tertiary alcohols. Most aldehydes will yield secondary alcohols, and formaldehyde will yield a primary alcohol. Okay, so if it reacts with carbonyl compounds, we also have a couple other carbonyl compounds we can react with. And in the case of an ester or an acid chloride, what we'll see is that we have to use two equivalents of an organometallic reagent. And when we do this, we'll generate a tertiary alcohol. So let's look at that reaction in a little more detail. So if we have let's look at our methylpropionate here. If we react it with two equivalents of magnesium bromide, methyl magnesium bromide, and then we quench with water, what we'll end up with is adding two groups there and removing the alcohol portion of the ester. So we'll end up with our tertiary alcohol plus our two methyl groups added on plus the original ethyl group we started with. Okay, so in the case of the ester reaction, the first step will add across that double bond and give us our intermediate anion with our first methyl group. Then what can happen is this can kick down and kick out a alkoxide ion right here. And when it does that, it generates a carbonyl compound right here. And then our second equivalent of our methyl magnesium bromide will come in and react with our carbonyl compound to generate our tertiary alcohol with our two new R groups on it. Similar mechanism happens when we use an acid chloride. When we use an acid chloride, what we'll see is that we will get our first step of our reaction where, let's use acetyl chloride here. The first step will generate our intermediate with our chloride ion, our oxygen anion right here. Okay. And then this will kick down and kick out a chloride ion, which is a nice stable leaving group right there, regenerating our carbonyl compound, where we'll have it attacked by another group of methyl magnesium bromide to generate our tert-butyl alcohol after quenching with water. Okay, so the key reactions we have with these organometallic reagents is we can ring open an epoxy, giving us a two-chain extension on whatever organometallic we have, a two-carbon extension on whatever organometallic we have. We can use ketones to make tertiary alcohols. We can use most aldehydes to make secondary alcohols. We can use formaldehyde to make a primary alcohol. And if we use two equivalents of an organometallic reagent with esters or acid chlorides, we can generate tertiary alcohols. That concludes section 3 of chapter 12.